Hi everyone, my name is Sergio Dorado-Rojas, a second-year PhD student at Rensselaer Polytechnic Institute, and this work, titled Synthetic Training Data Generation for Machine Learning-Based Small Signal Stability Assessment, was developed with my fellow PhD student Marcelo de Castro Fernandes and supervised by Dr. Luigi Vanfretti, head of the LSAT lab. This presentation is structured as follows. First, I will describe the motivation for this work from the perspective of power systems. Then some preliminaries will be introduced before jumping into scenario sampling for data generation, one of the main points of this work. Since the generated data has been employed to train machine learning modules for small signal stability assessment, we will go through some steps of the machine learning design and discuss their corresponding results. Finally, this presentation will be concluded highlighting the main contributions of our work. Before starting, I would like to thank Dr. Tetiana Bogodoraba for the insightful discussions that have improved the final presentation of this work. And I would like to mention that this work has been founded by NYSERDA in a joint project with New York Power Authority, and would like to thank as well the King Abdullah University of Science and Technology for their sponsorship. Simulations are used in our current modern electrical grids to assess the actual condition of the grid and also to study future behaviors. However, due to the integration of renewables and the complexity of the models, the amount of information or data that is coming out is larger than ever. So how do we interpret this large-scale data? Machine learning seems to be a method or a set of techniques that can be used to extract information from data, but some machine learning techniques are hard to interpret. How do we achieve machine learning explainability? Well, we generate the data from simulations, and we define some metrics that we can compute on a small scale, but we cannot do it on a large scale. So we would like machine learning to bridge us from this small scale data where we know the physical meaning of the results that we want to get, and then we will use machine learning to bridge us to the large scale. So before jumping into that, we will recall that machine learning can be defined basically as learning from data, and it has been successful in domains where data happens on a large scale, but we know that that is the case for power systems right now, because we have inputs like PMUs and simulations that are achieving such large dimensions, and we would like to find patterns and perform predictions. So our claim is that we can achieve the process of evaluating data, but on a massive scale now using machine learning based techniques. So what do we have? We have outputs from thousands or millions of simulations. And what do we want? We want metrics that we can compute on a small scale that can be used to assess the condition of the system. So here we will bridge from A to B using machine learning algorithms. And that is the scope of, that is the big context of our work. So the contribution of this work is threefold. We introduce an ad hoc Monte Carlo sampling technique to generate contingency scenarios for a power system model. Then this will be the data generated by this massive contingency simulation will be used to train several conventional machine learning algorithms and a neural network to assess the small signal stability of a power system. And then we propose a metric to quantify the performance of the classifiers and see whether there is a gain or not of substituting this domain-specific rule based on the damping ratio that we observe here on the right by a machine learning module. So let's start with some preliminaries, and the first one is to do a small refresher of what a small signal stability is. So perhaps the most famous textbook definition of a small signal stability was given by Kunder as the ability of the power system to maintain synchronism when subjected to small disturbances. But the picture I have in my mind about it comes from a microelectronics circuit, where we have here the picture of a static nonlinear system that we know that every system in real life is nonlinear. And for the case of dynamical systems, we know that this can be represented by a state space representation like this. So why don't we consider the case in which we have a linear approximation around an equilibrium, and we represent that approximation by a LTI system? So these matrices A, B, C, and D, we know that can be computed by taking the partial derivatives of f and j with respect to x, the states, and u, the input, respectively. And this approximation will be close enough to the real nonlinear system when we are working with this within this neighborhood of the equilibrium that is the region of validity. So in this case, what we would like to do, and the main reason of using small signal techniques, is that we can not only do a qualitative analysis of the nonlinear system, but also we can quantify some properties of the response due to small disturbances within this region. So for that, we will take the matrix A and we will study the eigenvalues. So the eigenvalues of A will produce some modes on the system. Basically, the modes have this form depending on the algebraic multiplicity of the eigenvalues. And these modes will tell us how fast the system is, but most importantly for power systems, how will the system oscillate when some disturbance occurs. So we would have to know the location of the eigenvalue, but there is a metric that is really special that can be computed and describes everything, and that metric is a scalar, and that is the damping ratio. So the damping ratio is a number, a scalar, that, for example, if the damping ratio is negative, we would have the eigenvalues on the right half plane, or if the damping ratio is between 0 and 1, we know that we will observe some oscillations in the system because the eigenvalues will be complex conjugate. So here we will use the damping ratio as a discriminative scalar metric. So this will be the way in which we will construct the labels that will help us to train machine learning modules in a supervised learning fashion. After having talked about the damping ratio as a discriminative scalar metric, it's time to focus our attention on scenario sampling. So how the different contingency scenarios will be generated. As a case of study, we propose the IEEE 14 bus system that counts with 5 generators, 16 lines, and 4 transformers between buses. So let's constrain ourselves to the case where we want to study line openings. And we know that there are 20 elements connecting the system nodes. So if we want to simulate a line opening, we could remove this element from the system model. But by doing that, we will be changing the number of states, or more precisely, the number of variables on the system. And we will be also modifying the topology of the grid. So in order to avoid it, we will take advantage of the fact that each of these elements, either lines or transformers, count with a transversal reactance under either pi or t miles. So if we make these reactances large enough, for example 10 to the 12, we would be emulating a line opening without changing the number of variables in the systems, nor the number of states, nor the topology of the grid. Now we should ask ourselves how the line openings will be selected. In this system, we know that we have n equals 20, so that is the total number of branches. And we would like to study the number of, so how many contingencies can we have if we open one line at a time? So k equals 1. So the total number of contingencies will be the combinatorial of n and k, given written here as n sub n s sub nk. And then it's logical that we will constrain the number of contingencies to those scenarios of practical significance only. So the minimum number of simultaneous tripping has to be 1, and the maximum has to be n minus 1. So for this case 19, because it makes no sense to study the scenario where we trip all lines. So the total amount of possible scenarios is given by this sum here, and for the IEEE 14 bus system, this corresponds to 1 million scenarios. So does this mean that we will generate 1 million scenarios and we will study 1 million scenarios? Well, no, because we know for experience that the scenario where we trip one line is more likely to happen than in a scenario where we trip 10 lines or 12 lines. So we need to account the fact that in real systems, small contingencies, so the trippings with lowest number of lines, will happen more likely than trippings of simultaneous lines at the same time. So to do it, we propose a two-stage Monte Carlo method, where on the first stage we select the number of lines that will be opened, and on the second stage we select from the pool of scenarios with k lines being tripped, we pick 1. So the first stage, the selection of the number of lines that will be tripped, we follow a modified Poisson distribution, like the one here. So this is the equation of that Poisson distribution. And on the second stage, once we have selected k, the number of lines that will be opened, we go to the pool of all contingency scenarios with that number of lines, and we pick randomly 1. So that the probability distribution for the second stage is uniform. And here we have the probability distribution function of the first stage. So this goes well with our intuition that scenarios with a low number of trippings will be selected. So basically all scenarios with 1 line tripping will be included into basically any study. Then for 2 and 3, almost all of them will be there. And we have done something for large systems to help scalability of the contingency generation method. It needs to trim the distribution at k equals n-5. So why? So the reason here is twofold. The first of all is that it is not likely that we will have 10 simultaneous trippings in a big system. And the second one is because of computational efficiency. So here on the left, we see that we have number of branches versus execution time. So this study has been done for different systems with different number of buses, states, variables. But here what is critical for this contingency generation method is number of branches. So here we see that as the number of branches grows, the execution time starts increasing exponentially around here, around 27, 28 branches. So we jump from less than 1 minute to 8 minutes. So to avoid this behavior and to allow our method to scale up for large systems, we have imposed that constraint of n-5, and then we have the result here on the right, where we see that, for example, for Nordic 44, a system with 79 branches, we can generate 24 million different scenarios using this method in less than 6 seconds. So that is really good, and it speaks really well of our contingency generation method. So data generation has been done using OpenIPSL and Daimola. So the model of the 14-bus system has built in this library that is an open source modular library for power systems. And I should do a small advertisement for our lab because we maintain the library. And this library contains a set of power system components for phase ordained domain simulation. And these models have been validated against commercial tools such as PSSE. So the procedure for data generation is firstly to select the scenarios using the Monte Carlo method that we had described in the previous slides. Then we set up the model by opening the branches, so that is modifying the transversal reactance value. And afterwards, we make use of the linearized model function of Daimola to get the analytic Jacobian. So not the numerical Jacobian, but the analytic Jacobian by derivating directly the equations of the model. And after we have the A matrix, we compute the scenario eigenvalues. And using the scenario eigenvalues, we can just easily, using the damping ratio, determine the labels of the classes. We repeat this procedure for 20,000 scenarios, but of course we didn't do it this one by one, but we have an automated process using the Python Daimola interface, that is the Daimola API for Python. So here we see the regenerations of data results for some cases, and we can detect some problems, some obvious problems that will, if they are not tackled here, they will get us some trouble in machine learning training. So first of all, we detect that there are some eigenvalues due to fast modes that are far away from the origin. After this, we detected as well there is like a concentration of eigenvalues here in the origin and here along the imaginary axis. So this could complicate the learning process because the neural network or the machine learning algorithm would not know exactly what the decision boundary is, especially the stability boundary, so the imaginary axis. So to solve this, we have proposed a data normalization distribution, but this is conditional because we don't normalize the eigenvalues inside the unit circle. So why? Basically because if the eigenvalues are here, yeah, or let's say if these are really close to the stability boundary, if we normalize them, we will be sending them all the way here to the unit circle. So they would be hiding, quotes hiding, the fact that they are really close to the stability boundary. So by doing this, we observe that we have some eigenvalues here in the origin, and then we can ask ourselves, well, this system is unstable, right? This scenario, the system in this contingency scenario is unstable. Well, that's not the case, and this is where domain-specific knowledge can help us, because eigenvalues at the origin are common in power systems analysis because of the swing equation in the electromechanical model. So in the electromechanical model, we have this relationship between angular speed and angle. So we need to integrate to go from one to the other. So we will have always these modes here. So these eigenvalues are not relevant for our analysis, and that helps us define another additional class or category. So let's go to the classes now. We know that we will use the damping ratio to define the classes. So the first of all is, of course, when we have an eigenvalue with negative damping ratio, we'll say that it's unstable. Then for eigenvalues having a damping between 0 and 5%, we'll say that they are stable, but they are critical. So the system operator would need to take some action to correct it. Then afterwards, we have acceptable, good operation, and satisfactory, meaning that, that the oscillations are low enough so that we can say that the system stability is not compromised. And finally, these irrelevant eigenvalues that correspond to some neighborhood here close to the origin. Okay, so let's now talk about machine learning techniques. So the conventional machine learning methods that we have benchmarked against the neural network are widely used classifying modules such as softmax regression, support vector machines, k-nearest neighbors, decision trees, and naive Bayes, and all of them were implemented and tested using scikit-learn. So for a more detailed reference, we point you to this excellent book by Aurélien Geron. And the neural network design is pretty simple, so it's just a multi-layer perceptrons with 4 layers and 2 dropout layers placed after the first and the second layers. And this intend to increase generalization performance and reduce overfitting. And now let's discuss a little bit of the results. So for the results, we have proposed this metric that tries to benefit the techniques with the minimum execution time. So when the execution time is the minimum, this term is the highest. And here we try to benefit those techniques having best performance in the testing set in terms of accuracy, precision, and recall. So here we have the results, and then we see here as expected that the damping ratio classifier gives us perfect performance at the expense of a slow execution time. Then the best performing technique is not the neural network, it's actually the k-nearest neighbors, but the execution time is the slowest. So we see that reflected here in the score, that the score is not that good, actually it's the worst. So the neural network gives us a balance. So it gives us really good performance, but with a really low execution time. So here we can see the results graphically. And the neural network, it's really good at the most critical part of this classifier, that is classifying whatever is unstable as unstable. The problems for the neural network comes here, where it misclassifies something that is good as critical, but that is something that we can tolerate in an application. So this can be quantified seeing the confusion matrix. So here we see that it misclassified something that is unstable. Unstable is the first category, so something that should be on the first category was classified on the last one, that is irrelevant. But if an eigenvalue is irrelevant, it's because it's close to the origin. So we can raise a yellow flag to warn the operator that something could be happening in the system. Then for the rest of the categories, we have a small misclassification error, but we have overall a clear decision boundary, and that is a virtue of the neural network. So to conclude our work, we have proposed a simple ad hoc Monte Carlo method to produce contingencies with physical meaning for synthetic data generation in power systems. And we have generated 20,000 scenarios via Modelica based models, and these scenarios have been used to train neural networks with the aim at analyzing automatically the small signal stability of the system. And among the methods that we have studied, we have seen that the neural network shows a balance between execution time that is critical for real-time applications and performance. So we would like to invite you to check the code for this work at these two repositories. And I would like to thank you for your attention, and I look forward to answering your questions at the Q&A. Thank you.